In this video, we will talk about null hypothesis significance testing. Now, what is null hypothesis significance testing? It's this procedure whereby you first posit a null hypothesis, that is, you assume there is no effect, your variables aren't related. Then you calculate the probability of an effect, assuming the null hypothesis is true. For example, an effect may have occurred by random sampling. Then you evaluate the unexpectedness of that kind of effect from the null hypothesis. And if the probability of such an effect is too low by some arbitrary criterion, then you reject the null hypothesis, thereby concluding that your variables are in fact related, that there is an effect. Could you ever be wrong in your conclusion? Of course you could. Nothing is ever certain. How likely is it that you will be wrong? This is something that can be studied statistically. The first kind of error is when your research hypothesis is actually correct, in which case the null hypothesis will be incorrect. You cannot know that for certain. If the null hypothesis is incorrect, then you should be rejecting it. But you only have your sample to work with, and your data may not allow you to reject the null hypothesis. Or your research hypothesis may be incorrect, in which case the null hypothesis is in fact correct, and therefore you should not be rejecting it. But you cannot know that for sure. You only have your data to work with. And based on your data, you may have to actually reject the correct null hypothesis. Let us look at this in a table. The first case is when the null hypothesis is false. That is when your research hypothesis is true, the alternative hypothesis is true, and your data lead you to reject the null hypothesis. In this case, you have correctly rejected the null hypothesis, and you are correctly reporting a relationship. The second good scenario is when your research hypothesis is not correct, so the null hypothesis is in fact correct, and you correctly fail to reject it. Your data lead you to not reject the null hypothesis, in which case you will correctly report that there is no relationship. However, it's possible, sometimes it will occur, that your hypothesis is false, but you nevertheless have to reject the null hypothesis based on your data. This is called a type 1 error. Conversely, if your research hypothesis is true, but you fail to reject the null hypothesis based on your data, then you are committing a type 2 error. Not very creative naming there. Now we have to be very careful when we say these things, because we don't know what is in fact true. We don't know if the research hypothesis is true or if the null hypothesis is true. We cannot even evaluate the probability that it is true, and that's why we have to resort to this cumbersome thing as null hypothesis significance testing. So we cannot calculate the overall probability of making any of these errors. What we can do is we can calculate conditional probabilities. So the probability that something will happen assuming a given state of things, so based on specific assumptions. For example, on the assumption that the research hypothesis is false and the null hypothesis is true. So on the assumption that there is actually no effect in the population, your data set may nevertheless exhibit an effect due to sampling. So you may get an extreme sample that is far from the population. You may get a non-representative sampling by bad luck. You have a criterion to limit this. That is your alpha level, your criterion for rejecting the null hypothesis. If you set your criterion at 0.05, such that you reject the null hypothesis whenever your p-value is less than 0.05, this means that you will be falsely rejecting the null hypothesis 5% of the time. Maybe we should pause and consider this a bit more. The fact that you're using a criterion to reject the null hypothesis set at 5% means that you will reject the null hypothesis whenever the effect, such as that observed, is less likely than 5% to have occurred by sampling from the null hypothesis. How often will this happen? It will happen exactly 5% of the time, because that's the whole point. But if you are rejecting the null hypothesis whenever you have obtained an effect that is less than 5% likely to have occurred by the null hypothesis, it means that 5% of all false research hypotheses are going to be accepted as true. 5% of all true null hypotheses are going to be rejected because that's your criterion. Effects that are less likely than 5% to occur by sampling from the null hypothesis will occur with frequency up to 5%. So we expect 5% of all false research hypotheses to be actually type 1 errors. In general, the type 1 error rate equals the criterion for rejecting the null hypothesis. So by defining the arbitrary criterion for rejecting the null hypothesis, we are effectively specifying our alpha level. The alpha level is also the rate of type 1 errors. If our research hypothesis happens to be true, so there is an effect in the population and the null hypothesis is false, you may still get no effect in your data because of sampling. You may have gotten unlucky and gotten an extreme unrepresentative sample that does not exhibit the effect seen in the population. Or the effect may have been too small to be discerned with the sample. Maybe you did get a representative sample, but the effect size is just very small. What exactly does that mean? The way to understand that may be to think of standard error as a kind of microscope that can be weak or powerful. Let's work through an example. For the usual alpha level of 5%, it is possible to discern an effect that is a relationship between two variables if the index of the effect is larger than approximately 2 standard errors. If the effect is less than 2 standard errors, then it will lie within the 95% confidence interval. And so you will not be able to reject the null hypothesis, even if the effect is reliable in the population. In the same way that you need a more powerful microscope to see smaller organisms, you need a smaller standard error in order to be able to discern smaller effects in the data. The standard error is what determines the resolution of your analysis. The standard error is given by the standard deviation in the population divided by the square root of the sample size. So if we're talking about a given level of variability, a certain fixed standard deviation of your measure in the population, it is sample size that determines how small differences you can possibly detect. It is sample size that determines how small effects it is possible to see with your statistical procedure. Here is the example. Let's say the measure in your population has a standard deviation equal to 10. A sample size of 25 implies that the standard error would be 10, that's the standard deviation, divided by the square root of 25, that's 5, so the standard error will be 2. The 95% margin of error will be about 2 standard errors, roughly. So 2 times this 2, that's 4. Any difference that is less than 4 is going to be statistically invisible because it will lie within your margin of error. So you will not be able to reject the null hypothesis. If you had a sample size of 100, then the standard error would be the standard deviation of 10 divided by the square root of 100, that is 1. The 95% margin of error would be twice this standard error of 1, so it would be 2. The margin of error would be equal to 2, so you will not be able to see any difference that is less than 2 because it would lie within your confidence interval and you will not be able to exclude it. But now you will be able to discern differences that are less than 2 as long as they're greater than 1. So the larger sample size allows you to see smaller effects. Let us also try a graphical explanation. Assume a null hypothesis with a mean of 0. This is the sampling distribution for this null hypothesis with a mean of 0, where we've set the standard error to 1 so that this axis actually can be interpreted as number of standard errors. If you are indeed sampling from the null hypothesis, that is, if there is no effect in your population, you've set your criterion, your alpha level, to 0.05, which means that if your sample happens to be in this 2.5% or in this 2.5%, then you will reject your null hypothesis and you will be making a type 1 error. So if you're sampling from the null hypothesis, you will be sampling somewhere here 95% of the time, but you will sampling outside this region 5% of the time. So that's your criterion and also your type 1 error rate. That was if the null hypothesis were true and you were actually sampling from it. What if the null hypothesis is actually false? The criterion is the same because you don't know if the null hypothesis is true, and you always have to assume the null hypothesis in order to set a criterion according to which to evaluate a p-value. So this is your null hypothesis, and this is your criterion for rejecting it. Let's say that in the actual world, there is actually an effect of size 3. So the sampling distribution for the mean for your measure is this one, centered on 3. So when you collect data, you are sampling from this distribution, the state of the world, and you evaluate it according to the null hypothesis because this is the only one you can calculate things from. You don't know this. So when the sampling distribution for the mean is 3 standard errors away from the null mean, as in this diagram, then your criterion based on the null hypothesis will lead you to reject the null hypothesis whenever you get a sample from this region. And your criterion will lead you to not reject the null hypothesis whenever you get a sample from this region. Obviously, if the actual effect in the population is 3 standard errors away from the null mean, then it's more likely that you will correctly reject the null hypothesis than to incorrectly fail to reject it. How big is this? Well, this turns out to be 85%. So the way these are drawn right now, the power to detect this true effect is 85%. Still, you will not be able to reject the null hypothesis 15% of the time, because although you're sampling from this distribution, which is 3 standard errors away from the null mean, you can still get a sample that is within this region, which is below the criterion set by the null. You can get unlucky, and although you're sampling from the population with this mean, you can get a very low mean, a non-representative sample that will not lead to rejecting the null hypothesis. What if the actual state of affairs was an effect of size 4? So the actual sampling distribution from the population was this one, and the mean of this sampling distribution was 4 standard errors away from the null mean. Your criterion is always here. The criterion is set on the null. So if you set the criterion at 5%, the same thing as before, this is where you cut things off. So if you are 4 standard errors away from the null mean, but you don't know that, you just have one sample, you'll get one sample from somewhere in here, but now all of this region would lead to rejection of the null hypothesis because it's outside the criterion. And only this small region would lead to incorrectly retaining the null hypothesis. That would be a type 2 error. So in this case, the power to detect a true effect would be 98%. It means that if the effect in the population is 4 standard errors away from the null mean, you will probably detect it with a probability of 98% by sampling from it. And you have a small chance of 2% of obtaining a sample that will not lead to rejection of the null hypothesis and will be a type 2 error. What if we have an actual sampling distribution at 2 standard errors away from the mean? So there's an effect in the population, but the mean of this sampling distribution, the mean in the population, is just 2 standard errors away. Well, the criterion is still here. So if we apply the same rationale for 2 standard errors away from the mean, we get a probability of rejecting the null only 52%. So if the effect is at 2 standard errors away, you're about as likely to reject the null hypothesis as you are to not rejecting. So there's a true effect, but you only have a 52% chance of statistically detecting it. The rest of the time, you will get a sample in this region, and you will not be able to reject the null hypothesis, so you will falsely conclude that there is no relationship, when the problem, in fact, is that your effect was just too close to the null in terms of how many standard errors away it was. If you used a much larger sample size, you would have a much higher probability of detecting the same effect. You can imagine that things would get much worse if the true effect was 1 standard error away or less. Then it will be almost completely invisible to this statistical procedure. Now, what exactly does it mean to be 3 standard errors away? Let's work through a couple of examples to see how this works. Remember that the standard error of the mean is equal to the standard deviation in the population divided by the square root of sample size. So if we're sampling from a distribution with population mean equal to 36 and standard deviation equal to 60, if you sample with 25 individuals, so sample size equals 25, then your standard error will be equal to the standard deviation of 60 divided by the square root of 25, that's equal to 12. So your standard error equals 12. If you divide the mean by its own standard error, the answer is 3. So the mean is 3 standard errors away from 0. In this case, we can calculate power for an alpha level of 5% to be equal to 83%. This means that you will be able to reject an effect, a difference in means at 3 standard errors away 83% of the time. Now we are talking about a true difference in means. If the population mean differs from the null mean by 3 standard errors, but of course you don't know where the population mean actually lies, so you will get a smaller or larger difference in your own sample. The point here is that if the true mean is 3 standard errors away, then 83% of the time you will be able to meet the criterion of less than 0.05 and thereby reject the null hypothesis. If you sample with 16 individuals, a very small sample size of 16, the standard error will be the standard deviation of 60 divided by the square root of 16 equal to 15. If you divide the mean by its own standard error, we see that the mean is now 2.4 standard errors away from 0. In this scenario, the power for detecting an effect at an alpha level of 5% is 67%. So if the true population mean is 2.4 standard errors away from the null, then you have a 2/3 chance of obtaining data leading to correctly rejecting the null hypothesis. If your sample size is 36, a bit larger, your standard error will be 60 divided by the square root of 36 equal to 10. So that will be 3.6 standard errors away from 0, in which case the power for the same criterion will be 95%. So you will have a 95% chance of detecting an effect if the true population mean is 3.6 standard errors away from the null mean. In general, power is the probability of detecting a true effect. So if the null hypothesis is actually false, the probability that you will be able to reject it is called power. It only makes sense in the scenario where the null hypothesis is false by definition, in the same way that the p-value makes sense only on the assumption that the null hypothesis is true. The power depends on 3 things: the variability in your statistic, how variable your statistic is, because you need that standard deviation on the numerator. So if your statistic is more variable, then your standard error will be larger. Therefore, your power will be lower. It depends on the sample size, which goes on the denominator in the square root. So if you have a larger sample size, you will also have a higher power, but the relationship is not linear. To have a substantial increase in power, you will need a very large increase in sample size. And of course, power depends on the criterion for rejecting the null hypothesis. If you have a very loose criterion for rejecting the null, then you will have higher power. If you have a very strict criterion for rejecting the null, then you will have lower power because the threshold will be higher before you can declare rejection. But if you have the loose criterion and therefore higher power, you will also have a higher type 1 error rate, which is something we do not want. You will be rejecting a lot of true null hypotheses in this case. So we never try to increase our power by using a less stringent criterion for rejecting the null hypothesis. What we do is try to minimize variability if it is possible, and usually just increase the sample size. So going back to that table of possibilities, we can now look at the probabilities which are conditioned on which hypothesis is true. If the null hypothesis is true, but you nevertheless reject it, and you make a type 1 error, that's your alpha level. This is, by definition, your criterion for rejecting the null hypothesis. So you are defining how often you will be wrong with true null hypotheses. Still being on this column, so still contingent on the null hypothesis being true, there are only two possibilities. Either you reject the null hypothesis, which is an error, a type 1 error, or you don't reject it, because the two probabilities must add up to 1. I mean, you will do something, either reject or not reject. The probability of correctly reporting no relationship is therefore 1 minus alpha, because 1 is the total probability. Moving on to the other column, in which the null hypothesis is false, and therefore the research hypothesis is true, the probability of correctly rejecting the false null hypothesis is your power. This is how power is defined. The probability of incorrectly not rejecting the null hypothesis is a type 2 error, and this probability is called beta. Because if the null hypothesis is false, you will either reject it or not reject it. Therefore, these two must add up to 1. Power is sometimes known as 1 minus beta. So these are the probabilities for the different types of errors, contingent on the null hypothesis being either true or false.